Hello, I'm João Domingos, and I'm the first author of Unlimited Vector Extension with data streaming support, which I will proceed to present. To begin with, our work is situated in the vector processing space. Many of the current computational workloads, such as data analytics and machine learning, achieve higher levels of computing performance through the use of vector processing. While conventional solutions such as Intel AVX pose serious limitations by using a fixed-length vectors, new ISCA extensions, such as SVE and RVV, improve by allowing for vector lengths to be chosen during the hardware design stage. However, we still consider that there are some limitations in the current scalable extensions. Let's consider ARM-SVE as it is used by the top Fujitsu Fugaku supercomputer. With the A times X plus Y example, we start by looking at the computational part, the float multiply and accumulate instruction. It is a direct match to the A times X plus Y operation. In ideal conditions, if the data was automatically available in the registers, we would only need this one instruction to compute the kernel, as anything more would be an overhead and contribute negatively for performance, particularly if the data was automatically provided in the registers, ideally without latency. There would be no need for explicit load and store instructions. Neither the address calculation, index iteration, and even loop condition calculation instructions, as these would be overhead and therefore a waste of computational cycles. While there are some solutions to reduce memory access latency, such as prefetchers that prefetch data to higher cache levels, these are not 100% accurate. Other strategies for out-of-order pipelines allow for latency masking, but these come with a heavy cost on resources. As an alternative to these limitations, our proposal is UVE, a vector extension with scalable vectors and support for data streaming, where we try to seamlessly integrate data streaming in vector processing, eliminating overhead instructions and optimizing memory access latency to achieve higher performance than the current available in the vector processing solutions. To step over the shown limitations, we start by removing anything we consider to be overhead instructions, which left us with a much smaller loop. Comparing this loop with the SVE code, we set at achieving a large reduction in code size. And we use the vector multiply and accumulate instruction to take care of all the computational parts and keep the branch instruction for control demonstration. It, however, could be removed by using hardware loop instructions, potentially even optimizing the execution even further. We are leaving this for future work. To allow for automatic data consumption and production, UVE requires a pre-configuration of the execution, where the streaming mechanisms are configured to automatically feed data to and from the CPU. However, this process is only done once before execution. During the configuration stage, each stream is bind to a specific vector register from U0 to U31 through a specific set of instructions. In this example, we also need to broadcast the value A to all elements of the vector register U0. This register is not coupled with the stream, as it was not configured as a stream. Later, during the execution phase, each read or write to a streaming register iterates the stream state. This is what we consider to be an automatic consumption and production, which in our design results in the destructive behavior where data is no longer available on the streams after each iteration. While this pseudo-streaming assembly could leave doubts from the extent or complexity of the streaming configuration instructions, we set to show the precise opposite. UVE provides a small but comprehensive set of instructions for register-register movement, arithmetic, and logic. We also support instruction predication, allowing for finer execution control. In the loop, UVE requires a small price to pay. Our definition imposes that the stream must be exclusively configured for loading or storing. which requires the vector multiply and accumulate instruction to be separated into two. UVE supports branch instructions dependent on the stream state, such as stream complete and stream not complete. This has the possibility for finer control over the execution through a new set of branch instructions that actually evaluate if a selected dimension has iterated. Taking into account the running example of AX plus Y, UVE uses significantly less instructions than SVE, and in this case is only a simple unidimensional memory access pattern. As a result of code execution simulation, we show that UVE uses significantly less instructions, in average 1.5 times less. It has the potential to further reduce the number of execution instructions in codes with complex memory access or difficult vectorization. We consider data streaming support to be the main feature of UVE, and to be able to define what we call a stream configuration, we need to start by considering the simplest unit of vector memory access, the unidimensional access. To make a stream out of this, we identify a set of essential parameters, the offset, the size, and the stride. While the offset defines the starting point, size represents the number of data elements, and stride specifies the spacing between such elements. We also add the data movement direction, whether it is a load or a store, and the data width, be it a byte, half, word, or double. With this, we completely define a single-dimensional memory access pattern. Our stream representation is very close to the C language for loops, where there is an initial offset, a total size, and an incrementation stride. UVE also comes with additional benefits. Passing from unidimensional memory access to bidimensional is simply achieved by providing one more dimension to the stream description. And cascading one instruction for each additional dimension, we achieve multidimensional representations. Going further, and by using modifiers, we can describe complex but still regular memory accesses, such as this lower triangular pattern, or even more complex scatter-gather and indirect patterns. The modifiers allow for inner loop parameters such as the size, stride, or offset to be dynamically adjusted based on the outer loop iteration, or even based on another stream's data. And all using the exactly same loop kernel. UVE does not put any constraints on loop unrolling, hardware loops, or other software-level optimizations. Plus, the UVE computational instructions are agnostic to the streaming paradigm, meaning that the streaming configuration instructions can be applied to any ISO. As I've shown the potential of UVE in code, we must look at our reference implementation to understand the impacts on the microarchitecture. The first UVE implementation target is an out-of-order processor model, based on the Cortex A76 processor and simulated under the Cycle Accurate Simulator GEM5. UVE requires only the addition of a new logic block to the core that we named the streaming engine. This hardware block is the main component of our streaming architecture. When receiving a set of streaming requests from the out-of-order pipeline, these are reordered and validated. Then, valid configurations are stored in the stream table, initializing the actual stream. At each cycle, the streaming engine selects the higher priority streams and iterates over them. This results in the generation of a set of address ranges. In the case of a load stream, the memory requests are generated and start in a synchronous wait for the data, that upon completion will be temporarily held in the load FIFO. When a store stream is being processed, the addresses are merged with data from the store FIFO, generating a store request. During the execution of our running example, the stream configuration instruction will be set up in the streaming engine as the new stream configuration. This is done in order during the rename stage. The actual stream configuration is sent to the streaming engine during the execution, when all data is available. In the case of a misprediction, the streaming engine state is rewind and the stream eliminated. As the data must be moved to the pipeline from the streaming engine, the consuming instructions register a request for data during the rename stage. Later, when the data is available, it is sent to the register file. Leveraging the register file in this way allows for branch instructions to detect the stream state without special interaction with the streaming engine, as the state is provided alongside the register. During data production, the instruction sets up the store request at the rename stage. Only after writeback, the streaming engine will receive the data, waiting for the commit signal to create the store request. To maintain memory coherence, the memory requests are passed to the load store unit. This solves memory access collisions and conflicts in uniformity for streaming and non-streaming memory accesses. UVE is also capable of directly accessing lower levels of the memory hierarchy for loads through the use of uncacheable loads, slightly improving the memory access latency and avoiding cache pollution. While the idea of UVE must be convincing, we have results to confirm our proposal. We use the represented set of benchmarks and a few more to evaluate both SVE and UVE. The evaluation was carried out on a Cortex A76 model inside the Gem5 simulator. UVE shows significant improvements over SVE execution performance. We measured an average of 2.4 times the speedup, showing the true potential of UVE. This is especially observed in the more complex cases like TreeSolve and KNN, whose memory access patterns are triangular and indirect. While memory copy is the worst-case scenario with only 1.2 times of speedup, it has limited potential due to the simple memory access patterns and low kernel computational complexity. We can observe a trend in performance that is associated to the increase in the memory access pattern complexity. Although stack speed does not follow this trend, this is due to the low performance in SVE execution. In sum, UVE is a new vector processing ISA that relies on data streaming to significantly reduce the number of executed instructions and provides 2.4 times of actual performance over ARM SVE. As the next steps, we are trying to improve software support for UVE by adding a complete compiler infrastructure with streaming and auto-vectorization support. Also, support for more complex patterns is on the way, alongside with an implementation in RTL. We are also studying on how to optimize the streaming engine resources and to reduce the overall hardware footprint. Thank you for watching, and please give a look at our paper, Unlimited Vector Extension with Data Streaming Support.